Hello, my name is Dr. Eric Landrum from the Department of Psychology at Boise State University, and you're watching my research methods screencast about populations and samples. This is a pretty important topic for research methods and scientific psychology, so let's get into it. Different terms used at different parts of the process of going from a population to a sample to a true experiment. So, as we typically do, start off with some definitions for framing purposes. A population describes all the potential relevant participants. Now, sometimes when students think about this, they think about the entire population of the state or the country, and that's actually not the case here. It's all the potential relevant participants. And so it might be third graders in a certain school district or psychology majors who are juniors or seniors, or Alzheimer's disease patients who participate in adult daycare programs, or so on. So it's a population, but it's fairly narrow and specific to the actual type of study that you're conducting. So here's just a kind of a reiteration of that point. It doesn't mean the entire population, just a population of interest. Now, the goal will be always to select a representative sample. And so, for instance, if I was interested in the attitudes and opinions of undergraduates at Boise State University, and let's just roughly say, for the sake of a round number argument, that there's about 20,000 undergraduate students enrolled during the fall and spring semesters. Ideally, I suppose it would be great to send out a survey and get a response from 20,000 people. That doesn't typically happen in nature, in reality. And so we desire to select a representative sample. So the goal might be, could I select 200 people who look very much like the population of Boise State University students in terms of key variables like gender or age or ethnicity or high school GPA or high school SAT, ACT scores, whatever. Could I study a sample of 200 from that population and then draw some inferences at the end of the process back to the population of 20,000? So that's kind of a very brief verbal description overview of what we're going to be talking about today. And also I've got some pictorial views of this as well. So we start with that big broad population. It's our population of interest, and our goal is to draw a sample. That is to test a small portion of the population who actually can be tested. And I think it's a pretty decent analogy to think about when people draw a blood sample. You go to the doctor's office, and the phlebotomist or the nurse draws a blood sample. You've got the entire volume of blood in your cardiovascular system, call that the population. We're going to draw a sample, and obviously we want that blood to be representative of all the blood coursing through your veins. And that's pretty easy. It's actually much more difficult to draw a human sample from a large population and ensure that that sample is representative, although there are certain things that we can do, certain procedures that we can employ to increase our odds of doing that well. So that sample is that small portion who could be selected and tested. A little bit slightly different terminology, the sample frame is the acquisition of the list of members of the accessible population. So for instance, if I was interested in that Boise State sample of 20,000 undergraduates, the sample frame would be once I had the actual list of members who are accessible. So for instance, the typical way I would do it nowadays would be by email address, but what if someone, for whatever reason, has changed their email and changed away from the default that the university would issue, or does not, or no longer has convenient internet access to check an email, or just never checks at all because they're not user. And so a lot of times what will happen is that if you send an email and some bounce back to you, you start with the population number, you subtract the bounce backs, and that's the sample frame. Of the entire population, we tried to sample the sample frame of those who are actually accessible. It'd be the same thing if you're doing a mailed survey and you had incorrect addresses. You had return to sender envelopes given to you by the post office. The sample frame would be of those who were reachable. What are the statistics available about that sample frame? So, random sampling is about the process of going from that larger population of interest to the sample, not from the sample to the experimental control groups. That's a different process we'll talk about at the end of this screencast called random assignment. So random sampling, when we use this, we try to use a procedure that attempts to eliminate any systematic bias in the selection process. So we know we won't do it perfectly. We know there's random chance operating, but we're going to try to be as systematic and as fair and unbiased as we possibly can. And there are some checks and balances along the way that we can use to see if that's happening. So for instance, if I had a population of people and I want to draw a sample, I might use a random number table or random number generator. I might look at the last two digits of their social security number or their student identification number. With a random number table, just go down that list in that row or column and then just try to match up students. So if I come across the last two digits and you match up with it, you're in the study. If I don't match up with it, you're not in the study. So that would be hopefully somewhat random and arbitrary. We could pull names from a hat. It would have to be a mighty big hat, but we could cut up little slips of paper with student names on them. We could get a tumbler like they have at the lottery, although one for 20,000 slips of paper, tumble that up and try to draw a name out of a hat one at a time. And if we did a good job with that, pages weren't stuck together, all that good stuff, hopefully we could come up with a fair and random sample. From a comprehensive list of folks, like we might get from the registrar's office, we might select every nth name. And that's not a typo. Nth means it could be whatever number. So if I wanted a sample of 200 Boise State students from a roster of 20,000, I'd be selecting every 100th name. So maybe I would pick name 1, name 101, name 201. And actually what we would probably do there, use a random number generator from 0 to 100, generate that random number, and then go every 100th from that point. Just so there we want to be as random as we can and avoid any systematic bias. We could also use stratified sampling to ensure critical characteristics from the sample. I'm not going to go into that too much in this screencast, but there's a nice little section about this in your textbook. So, if I know from the registrar's office that the population of Boise State is 60% female and 40% male, I would like to have a stratified random sample where it's also going to end up being of those 200 students, 60% are female and 40% of male. Now I want each male to have the exact same probability of getting into the study as every other male, and I want each female to have the exact same probability of getting to the study of every other female. But when it's all said and done, I can stratify on gender to ensure that my sample looks like the population with regards to that gender variable. So anything you can measure ahead of time, if you wanted to stratify on age, if you want to stratify on the county they came from within the state of Idaho or the state within the United States, you could stratify in that neighborhood, prior SAT scored, admissions to college. And so if I want to make sure that my sample looks like the population on certain characteristics, that's called stratification. We can generate a stratified sample. So if you look at this graphic from left to right, the population is the big broad circle. That's all the relevant participants. There is a sample within that population, and that arrow means we want to draw that sample out, just like the phlebotomist draws blood out of the vein. We want to draw the sample out of the population, and that process is labeled with the square box right there almost halfway through the screen, called random selection. Once we have that sample, then there is a separate process of random assignment. We've talked about that in other screencasts, like the between and the within. We've talked about matching and blocking and randomization. That's how we can get into our two or more groups of the independent variable manipulation, experimental control. So there's randomness involved with both random selection and random sampling, but it's really important that you understand that those are really two separate processes that occur at different parts of the overall research process. And we'll keep coming back to this graphic a couple more times in this screencast. So in that random sample, each participant in the population being considered should have an equal chance of being selected. And I'll say that a couple different ways because it can kind of manifest itself in different ways. The selection of one person should not influence the selection or non-selection of the next person. And so, in other words, there shouldn't be any contingency. And so, if I select one person out of the sample of Boise State students, that should not disqualify any other student from being selected who's still in the population. So they should be relatively independent and not influencing one another. Again, that's that notion on the left-hand side of this of drawing the sample from that already exists within the population, drawing it out, and then having that smaller sample. So for the Boise State example I keep using, think of that larger circle as the population of 20,000 undergraduates, but think of that smaller circle as the 200 people I want to sample to do my study, to conduct my survey. So at first, that sample of 200 resides within the population of 20,000, but eventually I'm going to draw it out, and I'm going to study that sample of 200 very carefully. So there are a couple of major techniques with regards to random sampling. I'll be honest with you, they sound a lot more complicated than they are. And I actually think I've got some fairly nice graphics coming up for you that'll make it really clear. So sampling with replacement means that once you sample someone, once you draw someone out of the population into your sample, you actually leave them in the pool of the population where I suppose in theory they could be selected again, although you'll see in the example I give you, the odds of that, depending on the sample size, are pretty darn small. Actually, it's depending on the population size. The probability of being drawn twice from the same population is pretty darn small. Thus, every name in the population has the same probability of being chosen every time a selection is made. It would be like if you had a deck of cards, you shuffle the deck of 52, you say take a card, any card, you pull a card, and then you give it back. The dealer shuffles again the deck of 52, and you say take a card, any card. That's sampling with replacement. You put the card back in the deck. In this case, we're going to put the name back in the population. So in theory, it could be sampled again. You'll see why, in essence, it really doesn't make a difference that much, especially if the population is large. So here is a little graphic for you. I'm going to continue with my university sample here. So this is about sampling with replacement. It's your individual probability of being selected. So out of a population of 20,000, on the very first draw, remember I'm going from the population to the sample. On the very first draw, your chance of being selected is 1 out of 20,000. Hopefully you have an equal chance of being selected of all other 19,999 students. Okay, I'm going to draw a name. It might be yours, it might not be yours. I'm going to put that name back in the hopper. All right, I'm going to do a second draw. Your probability is still 1 out of 20,000. I'm going to put that name back in. I'm going to draw again. Your probability is also 1 out of 20,000. And I'm going to keep doing that, sampling with replacement, putting your name back in every time. I'm going to keep doing that, doing that, doing that. When I get to the 200th draw, because I want a small n of 200 in my sample, when I get to the 200th draw, your probability is still 1 out of 20,000. Every name I drew, I put back in the hopper, so to speak, and so that's 0.00005 in terms of probability, or 0.005% chance of being selected. So very minuscule, okay, 1 out of 20,000. And so, and by the way, if you want to think about it, the odds of your name being drawn twice out of this scenario is 1 over 20,000 times 1 over 20,000. It's infinitesimally small probability that you would be selected twice. So in other words, odds are I could probably just keep all the names in the hopper and not have to adjust every time I sampled without replacement. I could just use sampling with replacement. That would be fine. All right, so you put the name back in the hopper, you keep drawing. Odds of that you being drawn once are really rare, but twice it's almost astronomical, if not astronomical. That's sampling with replacement. You can preview it already. You can see where we're going. Another way to do random sampling is sampling without replacement. That is, a previously selected name cannot be reselected and must be disregarded on any subsequent draw. And I hope you can see where we're going with this. We're going to come back to our table. Oh, by the way, before we get to that table, there's a whole bunch of other options. I'm just giving you a few here. Again, digging into the textbook will give you a chance to see a few other options with regards to sampling from a population. So here, this example now will be sampling without replacement. Again, your individual probability being selected. On that first draw, it's the same as sampling with replacement, 1 out of 20,000. I draw a name. It might be yours, it might not be yours. I'm not putting that name back in the hopper. On the second draw, if you weren't selected on the first one, your probability, your chances are 1 out of 19,999 remaining names. On the third draw, your chances are 1 out of 19,998, unless you were chosen on the first or second draw. Then your chances are 0. By the time I get to the 200th draw, your chances are 1 in 19,801 because I want 200 people in my sample. So you can see that your probability did increase compared to the last slide, or the last version of this slide for sampling with replacement, where it was 0.000005. Well, now it's 0.00000505. It actually goes up slightly, but that's really not a lot. All right. However, in this scenario, there's no chance of you being selected twice, because if you're selected once, you're out. You're not put back into the hopper, back into the pool, back into the population. So that's sampling without replacement. So with large samples, to be honest with you, it really doesn't make much difference. But if you had a small population, like a population of 100 or 50 or 20, and you're going to try to do a true experiment with that small sample, then the technique might very well make a difference. Very briefly, just a little snippet about estimation. This is pretty much enough to get us through research methods, but obviously this is a much more complex topic. We use estimation to try and determine the characteristics of the population by studying that sample. That is, in our scenario here, we're going to try to study the 200 people in the sample and then estimate those characteristics back to the population of 20,000. And so we want to be careful about that, because when we make that inference from 200 to 20,000, we are exposing ourselves to the chance of making an error, of making a mistake. And so there are some fairly precise rules in probability and statistics that we use to follow that. The purpose of random sampling ultimately is to obtain a representative sample so that population parameters can be estimated. And so we're going to narrow our focus here in a minute from sample statistics as they're related to population parameters. So for instance, when I calculate a mean or an average, an X bar, like let's say out of those 200 people, I wanted to calculate the average age, all right? So the average age of that Boise State sample might be 26.2. But if I wanted to estimate that back to the population of 20,000, there's a chance it could be off. There's a chance it could be wrong. And so that estimate is a difficult process to make, although there's ways we can do it. If I had all 20,000 available to me and I had their ages, I could just calculate the exact age, and that's not an estimate at all. So parameters are calculations based on the entire population, and statistics are calculations based on the sample you have available to you. And I'm going to show you this on more screens as we go. And here it is. So statistics describe a sample. We're going to calculate statistics to estimate those population parameters. And so again, if I had all 20,000 and they'd answer my survey, I wouldn't need statistics. I could just calculate what I needed to. There'd be no leap from the small group of 200 to the large group of 20,000. I'd already be at the 20,000. By the way, we do this all the time. When there's national voting in the United States, there are companies that do a very good job looking at 1,600 registered voters and how they voted at the polls during that day, and asking them after they vote who they voted for. And they can make a pretty decent estimate from about 1,600 voters to the population of possibly millions and millions of actual voters throughout the US. And so they study the sample to draw inferences about the population. So just to kind of get ourselves used to the language, we use statistics from a sample to estimate population parameters. And here's a nice little table. And so you can see the statistics are in the left frame, the parameters in the right frame. And one of the things I want you to notice right away is that the sample statistics, those symbols are Latin or Arabic, our typical alphabet. On the right frame, the parameters are Greek letters. So when we are calculating the sample mean X bar, that's our estimate of the population mean mu. Sample standard deviation S is our estimate of the population standard deviation sigma. Sample correlation R there at the bottom row is our estimate of the population correlation rho. So for the most part, we're going to be calculating statistics, which are going to be these Latin or Arabic letters that we're used to, but we're really trying to make an estimate back to the entire population. And if we had the population available, when we make those calculations, they would result in parameters that are signified by Greek letters. So, descriptive statistics are those numbers which describe, summarize, or condense data. These are typically our measures of central tendency and variability. We use these for both descriptive and experimental research. So, for instance, as a quick reminder, measures of central tendency, mean, median, and mode. Measures of variability, range, variance, standard deviation would be common examples. So if the average age of the students enrolled in my research methods section this semester, that would be a descriptive statistic, all right? I could get the mean, I could get the standard deviation, I could have the youngest, the oldest, the max, and the min, and so forth. And so those would be kind of a snapshot of a known finite sample. And so it's not all the students enrolled in all research methods. It's not everyone enrolled at Boise State. It's a finite number of participants that I can calculate with probably pretty good accuracy the mean and the standard deviation. I can just, and that will help me describe to others the key characteristics of the sample that I am studying. And also it might help me make an inference back to whether or not this sample looks like the larger population of interest, whatever it might be in that study. Inferential statistics, on the other hand, are a whole other class of statistics that are calculated based on the sample, but the ultimate goal is to make that inference, that leap, that generalization back to the entire population. So we might be able to calculate X bar, but sometimes we really want to know mu. Well, X bar is going to be our best estimate of what mu, the population parameter, looks like for the entire population. All right. And so whenever we use an inferential statistic, we're making a leap of faith and there's a chance we could be wrong. There's a probability we could be wrong. And so I've got my small sample of 200. I want to make an inference back to 20,000. I'm going to make that leap, that generalization, that inference. And however, there's a chance that it could be wrong. So in psychology and in the sciences, we tend to call this p-values. Although if we were talking to our colleagues over in political science, they would call it margin of error. Okay, so we're going to make a leap, but we're going to admit we might be wrong. There's some wiggle room. So you project a candidate is going to get 43% of the vote, plus or minus 6% is a margin of error. Okay, that might be an erroneous inference. Okay, same thing with social sciences and in psychology. We're going to make a leap of faith, but we're going to admit there might be an error, and we're going to be talking about p-values a little bit in this screencast, but much more in screencasts to come. So, just a very brief, incredibly brief overview about probability, because it does come into play when we're doing hypothesis testing, thinking about p-values, drawing an inference from a sample to a population. So probability really talks about the ratio of favorable outcomes to the total number of possible outcomes, assuming that random chance is operating. I've got a bunch of examples here for you. So if you have a fair deck of cards, every card is there. There's no damage. There's no trickeration. If you have 52 cards and you've shuffled them, the probability of drawing the ace of spades on one draw is 1 divided by 52, or that's the same thing as 0.019. That's the proportion. If you want to turn that into a percentage, multiply a proportion by 100, that would give you 1.9%. So roughly speaking, the probability of drawing ace of spades out of a fair deck that's been shuffled, roughly speaking, is 2%, but precisely it's 1.9%. Okay? The probability of drawing any spade out of a fair deck, there are 13 spades in the deck, it's been shuffled, the probability is 13 divided by 52. As proportions, that's 0.25, that's a quarter, or you could make that 25% by multiplying proportion by 100. So I think you see the gist here. It's going to be that ratio of favorable outcomes to total possible outcomes, assuming that random chance is operating. So when we say things like p less than 0.05, or even in this case p equals 0.05, when we say 0.05, that's a proportion. We mean the same thing as 5 times out of 100, or 1 time out of 20, or 5%, or a nickel out of a dollar. And that's really about the depth of probability that we're going to get into that we really need for the most part for research methods. And so that p-value is a probability, and zero point 0.05 is kind of the gold standard, and we'll talk a little bit more about that in a future screencast. But I just want, when you see that 0.05, I want you to think of 5 times out of 100, or 5%, or even a nickel out of a dollar, whatever analogy works for you. That's the one I want you to use. Now, so we draw to the conclusion of the population and sample screencast, I want to come back to that graphic here eventually. So random assignment only occurs after we've drawn our sample. So imagine that phlebotomist in a blood draw, they might draw a vial of blood, but the lab might split that out and do 3 different tests on 3 different subsets of the blood that was drawn in the vial from the phlebotomist. Well, random assignment is going to occur after the sample has been drawn from the population. And here's where, and for example, in our between groups screencast, we talked about matching. In the within group screencast, we talked about blocking. And so now once we've got our sample, so for instance, if I draw in my population 20,000 students, my sample is 200 students, now how do I split that out into 100 students who are going to get the experimental intervention and another group of 100 students get that placebo control? How do I split my sample into the groups I need to test my hypotheses? That's what random assignment is like. And just like we need to avoid bias previously in the process, we want to avoid bias here. We want the only differences before we introduce our independent variable in any study just to be due to random chance alone. 2 groups of 100 people will, by definition as human beings, have some inherent differences built into them. We just don't want the differences to be biased toward or against our hypothesis. We'd like those biases to be irrelevant to our hypotheses. And so, and that's where we need to know our knowledge of the literature and how to design research and how to draw conclusions. And eventually, trust me, it all comes together in the end. Another way to say that, it all comes out in the wash. And so we want to be as fair as we can as we're divvying up those folks from the sample into our other conditions. And that's the latter part of this left to right. You can see random assignment in the square box happens as the sample is split into those 2 rows, the experimental group and the control group. So we want that to be random, and we could use some of the same techniques, random number generator, pull names from the smaller hat now. We could use matching, we could use blocking, we can use pure randomization. It might work depending on the sample size. So some of the techniques might be similar, but the process is different because it happens at a different point along the way. All right, that's it for populations and samples in our research methods course.